Hello everyone, my name is Mihai Frâncu and I will present you the paper entitled Locking Proof Tetrahedra, which I wrote together with Arni Askersson, Mats Rono and Kenny Ellerben. The main motivation behind this paper comes from the emergent field of soft robotics. Such soft robots are often built from silicon rubber, which is an incompressible material. Simulation of soft robots involves complex multi-body scenarios like pneumatic or cable actuation and interaction with the environment. As we are dealing with soft bodies, one usually resorts to the finite element method, or FEM, for simulation in conjunction with constraints. Constraints may arise due to very stiff material parameters, rigid bodies, or contact. Usually, such stiff constraints are accompanied by an unpleasant phenomenon called locking, which we will discuss briefly. Most people choose to work around this problem or simply ignore it. We will address it using mixed FEM. There are many works in mechanical engineering covering incompressible elasticity, locking, and mixed FEM, but not so many in computer graphics. We do mention the paper by Irving et al., which is the most similar to ours despite using many linear models. The paper by Pedersen et al. Is one of the few using mixed FEM in the context of hexahedral elements. A more recent paper by Smith et al. Covers simulation of incompressible media using a penalty approach. Our main contribution is the avoidance of locking for nonlinear FEM using tetrahedral meshes. Actually, our result is not only limited to a certain type of elements or interpolation functions, but it is based on the very general theoretical framework of mixed FEM. This allowed us to define generic discrete constraint functions, Jacobian and compliance matrices. We derived two numerical solvers for the resulting discrete problem, one using the Newton method with line search, and the other one using the augmented Lagrangian method, or ALM. Due to lack of time, we will not be covering them in detail in this presentation. To understand better our motivation, let us start with the example of an inflating rubber tube. We found that with first-order FEM with an Enochian material, the tube inflates very little when the Poisson ratio is close to 0.5. Increasing the order partially fixes the problem, but at a cost. Our solution was to use the mixed FEM formulation of FEM, which always avoids locking under certain discretization conditions. As you can see, the tube inflates much more. We found out that even for moderately coarse meshes, the results are close to reality. And we are guaranteed to always converge under mesh refinement. To better understand volumetric locking, let us look at a simple 2D example. The red and blue triangles are trying to keep their area constant. Only the top right hollowed node can move. For the red triangle, it can only move vertically and only horizontally for the blue one. So the two triangles block each other, resulting in locking. In general, locking is the byproduct of discretization and very stiff parameters. The solution boils down to counting the remaining degrees of freedom, as you can see in the bottom equation. This is only a necessary condition. Our proposed solution satisfies it and produces accurate deformation. On the other hand, is that it does not satisfy the sufficient condition known as LBB. We will briefly touch upon the consequences later. It is very hard to go into all technical details in this presentation. Therefore, I prepared an overview of the different paths taken to solve the elasticity problem. Nonlinear elasticity in continuous media is often posed as a variational problem. One must make a functional pi stationary under variations of the fields involved, deformation and stress in this case. There are two ways of doing this. The standard one substitutes the stress-strain relationship directly in the equations, and we get what is called the irreducible form, meaning there are no more substitutions or reductions possible. This usually leads to the numerical problem of unconstrained minimization. The mixed formulation, on the other hand, keeps the explicit stress field and the constitutive law accompanying it as a separate equation. In the most general case, this leads to a saddle point problem. But if the stiffness is very large, we can recast it as a minimization with hard constraints, like full incompressibility. For the sake of generality, we focus on the saddle point. The saddle point problem we are dealing with is a nonlinear one. A function called the perturbed Lagrangian needs to reach both a minimum and a maximum. One can use ALM to solve it numerically, but most other methods rely on successive linearization of the problem and eventually boil down to solving a linear system. The system can be either the original one, aka the KKT system, or it can be one of the two possible Schur complement systems. Please consult the paper for all the nitty-gritty details. Let us briefly introduce some nonlinear elasticity notation. We'll let you find the rest in the paper or in a textbook. The deformation field, denoted by small x, has a gradient f which dictates all the elastic behavior. The green strain tensor E is a function of f, and, more importantly, the energy density psi is a function of f for any hyperelastic material. Work conjugate to f is the first Piola-Kirchhoff stress tensor, meaning it is the derivative of psi with respect to f. The determinant of f also controls how a small element of volume evolves. We will call it J from now on, and it is simply a scaling factor. Of course, for incompressible materials it has to stay 1 at all time and for every point in space. We distinguish two types of deformation. Distortional deformation, which leaves the volume constant, see the top picture, and volumetric deformation, which shrinks or scales up the volume in all directions, see the bottom picture. This allows us to split all important quantities, like the deformation gradient or stress tensor, into a distortional and a volumetric part. More importantly, we get such a split for energy, as described in the mathematical box. This distortional energy only depends on the distortional gradient f hat, whose determinant is always 1, and the volumetric energy only depends on J. This is the ideal case of an uncoupled material. However, in practice, we found that uncoupled materials are not rest stable, meaning that at equilibrium we get a non-zero force. So, we chose instead to use uncoupled materials. Please refer to the paper on how to choose the volumetric and distortional parts of the energy. Another ingredient we need is a constitutive law. You start with a constraint function like j minus 1 equals 0, and then you build a quadratic penalty potential function. The pressure is given by the derivative of this function. Finally, we can invert the pressure function to obtain a relationship between the constraint and the pressure. This is otherwise known as a soft constraint or a regularized constraint. We can now derive the mixed weak formulation of nonlinear elasticity. It is nothing more but the conservation of the momentum plus the constitutive law. The derivation steps involve taking the variation of the total functional pi with respect to positions x and pressures p. This total functional is very similar to the Lagrangian of a constraint optimization problem. Here, the pressures p play the role of the Lagrange multipliers, enforcing the incompressibility constraint phi. These equations are not so different from the standard FEM ones. After the FEM discretization, the dynamic problem becomes an ordinary differential equation with algebraic constraints. We can now apply a numerical integrator and finally obtain the saddle point problem. Note that a very similar form is obtained in the quasi-static case. A lot of problems in engineering reduce to this linear system one way or another. The system is quite large and indefinite and can be even singular at times. Therefore, a lot of effort goes into efficiently solving it. We are using linear shape functions for both the displacement and the pressure fields. This means that compared to standard FEM, we need to store an extra scalar value per node signifying the pressures. This is the cheapest solution to locking. In standard FEM, pressure is not an explicit variable, it is in turn computed from the displacement gradient, making it constant per tetrahedron. Our mixed FEM solution guarantees locking-free and accurate deformation. However, both standard and mixed FEM using first-order displacements are prone to giving inaccurate pressure solutions, and this is due to not satisfying the LBB conditions. The implementation was done in C++ with custom-written solvers. Most of the time we used the Newton method with line search and direct solvers for the linear system. As expected, we found mixed FEM to be more expensive to solve than standard FEM, which has a smaller positive definite matrix. For some stiff scenarios, we found that standard FEM requires very small steps in the Newton line searches, making it very expensive to converge, whereas mixed FEM had no problem. See the plots on the right. On the other hand, we found other cases where mixed FEM had trouble converging. Therefore, solving the nonlinear saddle point efficiently is still an open problem. To sum up, let us compare our mixed FEM solution to standard FEM, both using first-order tetrahedra and nonlinear neo-Hookean materials. Our method performs much better in terms of locking, even for coarse meshes, and Poisson ratios of up to exactly 0.5. It can fail though when computing the pressure. This phenomenon is called checkerboarding and it is described in more detail in the paper. In mixed FEM, the condition number of the system matrix does not increase with the stiffness. Still, we found it sometimes hard to solve the saddle point problem. And of course, the saddle point system is a much larger one. Let's talk about some results now. This cantilever shows very well how standard FEM using a neo-Hookean material can completely lock. This happens for very high Poisson ratios, which are quite common for materials like silicon rubber. Our method performs the same for all values of the Poisson ratio. Also, the mesh resolution is not very high, less than 1000 tetrahedra, and this is a quasi-static simulation using a Newton solver. The results for the cantilever in the tube allowed us to go on and simulate other types of air chambers for pneumatics of robots. Here are 3 examples that all inflate more than standard FEM. Note also that above certain pressure values, Newton has problems converging in standard FEM, but unfortunately even mixed FEM cannot handle too high pressure values. This is most probably due to numerical issues and material modeling aspects, which are quite known in the mechanical engineering literature. Another difficult case for incompressible materials is that of a rubber block being compressed from the top. Here we use the FEBio open source software for comparisons. Our method can handle moderate pressure, for which standard FEM works too, but may require many line search steps. But for much larger pressure values, we had to use a special material and an augmented Lagrangian solver in FEBio, whereas our method could handle it without any modifications. Again, for higher pressures, both solvers start having numerical problems. Finally, we used our method for scenarios that are more common in computer graphics and much lower Poisson ratio. Here you can see a cat model falling down some stairs. Collisions are implemented using a simple penalty approach for now, and for more examples, please consult the paper and the accompanying video. So in conclusion, our mixed FEM method offers locking-free simulation at a relatively small price. It is still not as fast as standard FEM, but is often more stable, although there are still cases where mixed FEM behaves poorly. There are of course many future directions for extending the current work, among which we mention further numerical optimizations, full stress, tensor mixed formulation, maybe the free field mixed formulation, contact formulations using complementarity, and maybe investigate more the connections to position-based dynamics and projective dynamics. Finally, we would like to thank all of our collaborators, the reviewers, and the funders. Thank you for watching, and please do not hesitate to contact me for any questions you have.